It's really exciting to be here with all of you today and to see so many people here in attendance. As Hayden mentioned, my name is TJ Sego. I'm an assistant professor of medicine at the University of Florida. But before moving down to Gainesville, I worked in James' lab for 3.5 great years. We weathered the pandemic together, which was fun. And yeah, today we're going to do a session together on the Python API. If you don't know what an API is, that's totally fine. We're going to start from the ground up and hopefully try to give you a sense of why you might be interested in working with CompuCell purely in Python, what sorts of benefits and advantages such an approach might have for some of your work. And then, excuse me, and then we'll get into at a somewhat of a high level what all you can do in Python with CompuCell. Um, and then after that, we're just going to get right to it. We'll dig into the code. We'll do some coding together, some materials prepared, and we will start from some blank source code. And if all goes reasonably well, then we will end up with a working CompuCell simulation as you have become familiar with it through this workshop, but instead purely in Python. I'll try to keep my eye on the chat as best as I can. And of course, there are others here who can address questions and help as we go along. But let's go ahead and get into it. So much of the motivation for the Python API is to provide features and capabilities and support simulation applications and workflows that are really not obvious how to do in Player, if not just downright impossible. It is possible to do parameter sweeps in Player, for example. So for a parameter sweep here, meaning that I want to take my model and execute it while changing, say, one parameter to observe what the effect of that parameter is on the emergent behavior. That is possible in Player, but doing so is non-trivial and sometimes quite difficult. Whereas just working in scripted Python, it's a fairly trivial exercise. The same is true for batch execution, say on a supercomputer. So if you have access to high performance computer, say like here at the University of Florida, we have Hypergator, with lots of CPUs and GPUs at our disposal. Leveraging that technology in Player, I mean, you really have to jump through hoops. Whereas working from the Python API and using CompuCell in pure Python, deploying on a supercomputer is also as difficult as deploying really anything else from Python on a supercomputer. Um, and then there are all sorts of other things where Player just really doesn't support CompuCell deployment at all. So it's there is a trick to be able to run multiple CompuCell simulations simultaneously in Player, but we don't even document it because it's so complicated how to do it. Um, and integrating CompuCell is something like an integrated component in a workflow. Say you're pulling in a stream of data from some experimental data source, and you want to do all sorts of data processing and simulation and post-processing and whatnot. Player is just really not the tool for that. Whereas using CompuCell as an integrated component in Python, um, it certainly becomes possible to use CompuCell in all sorts of interesting ways. Now, to give you a bit of context for how this feature set falls within the scope of what you've learned to date. So, technically speaking, you all have been working with the Python API for as long as you've been working with CompuCell. So the steppables that you have been using to do, say, data analysis or implementing, custom models or whatnot, those steppables are really just one feature of a broader API in Python. And much of what we'll do today is really just introducing you to the rest of what you can do in Python using CompuCell. Um, which really is to say everything that you can do in Player, maybe there are a few exceptions, just about everything you can do in Player, you can do in the Python API, plus much, much more. And you can see a couple of examples here that I've included here on the right. So this is from some work that some of us did on an application modeling viral infection. And each of these panes here, these little subplots, each of these represents 10 simulation replicates. Uh, Doing this many simulations one by one in Player would be a week of your time gone easily. Whereas this was coded up in the Python API thrown on Indiana University supercomputers, and I think I executed all of these over lunch. So it's a big bump in productivity and being able to use computing resources that you may have at your disposal. But to take it one step further here in the bottom right, so this is an unpublished exercise that I did when doing some testing for the Python API. This is actually integrating CompuCell as a model in a parameter optimization problem using Python's SciPy package. So this is just a simple optimization problem, single cell migration. Each of these vertical columns, these are snapshots of a single cell migrating from the lower horizontal line to the upper horizontal line. And the problem is for a given fluctuation amplitude, find the corresponding chemotaxis parameter that puts the cell at that line. Now, all the details of that are totally irrelevant at this point, except to say that this is using CompuCell as just a generic Python function, and then plugging that into a SciPy optimization problem in otherwise a totally typical way. Now, I'd say the overarching goal more than anything with the CompuCell Python API is to make CompuCell function like a multi-scale, multicellular simulation library in Python, and really in strict terms. So this feature set makes CompuCell work like a Python library, just like the other Python libraries that you may have imported into your Steppables scripts. Import NumPy, import SciPy, import CC3D. Now, everything that goes into a CC3D simulation that you've been working with, there are analogous features in the Python API where there really is a one-to-one mapping. The features that you'll define in or use in the Python API for CompuCell, your model specification, your simulation details, they are quite literally the exact same thing as what you've been specifying through the CC3D ML and the Python Steppables. It really is just two ways of doing the same thing. And both produce the same kinds of simulations, whether you specify a simulation with the XML or you specify it with the Python API, both of them are really just two different ways to generate the same simulation data, the same simulation engine, and that produce the same kind of simulation data. Much of the goal is to give you, the user, the model developer, say the software developer, the ability to orchestrate simulations, much like what Player already does for you when you press play to launch and run a simulation. It's just that through the Python API, now suddenly you have control of all of the business of instantiating and running a simulation. So this is very much what Player does for you that you can then do yourself in Python and control along the way. So it's as basic as creating a simulation, giving model specifications to it, like the contact plugin or volume plugin, do some startup, and then execute a number of simulation steps until the simulation is finished. Now, to put this into perspective, though, when you do this in the Python API, you can do all sorts of additional things along the way that may be particular to your specific problem or workflow that you're developing. So, for example, when you create a model specification like the volume plugin, you can do additional things like, say, pull new model parameters from some external algorithm, like an optimizer. When doing simulation startup or stepping the simulations, you can do things like reload visualization configurations that say you or your friend previously generated that you'd like to reuse. You can check all sorts of external termination conditions for stopping your simulation conditionally or updating visualization based on the state of the simulation. And as far as concluding a simulation, You can do this conditionally based on the way that CompuCell has been deployed in your particular application. So there's just lots more that you can do along the way. Doing just about all of these things. Players, not obvious how to do this, whereas with the CompuCell Python API, we want to make being able to integrate these sorts of steps along the way with using a CompuCell simulation and otherwise a sort of typical way. Now, I'd like to go ahead and get everyone into a state where they can at least attempt to code along with me. We're going to learn and code simultaneously to the extent that we can reasonably get people set up to do so. I'll say that some of this work is non-trivial. If you're not particularly adept at Python or you feel like you're more focused on just trying to keep up than actually, absorbing the information that we're going through, I would strongly recommend that you just sit back, relax, enjoy the show. The slides will be uploaded or recording, so you can go back and review this at your own pace. Please don't lose out on the message for the sake of just trying to type what I'm typing and make it execute in the same way in real time. That being said, the CC3D Python package is either installed on your computer using one of the installers that you downloaded from SourceForge, either the Windows installer or from Mac or Linux. Or if you do like me, you just install directly from Conda. What we need to accomplish for each of you who want to try to follow along is to get Jupyter Notebook launched on your computer with CompuCell accessible. So you can do this in a couple of ways. So if you just installed from Conda directly, then whatever Conda environment you installed CompuCell into, all you need to do is open up a terminal and activate the CompuCell environment. So for example, I'm on Windows and one of my Conda environments is CompuCell3D. Conda activate CompuCell3D. And you're good to go. If you used one of the SourceForge installers, then you need to open a terminal. Thank you for the feedback about the terminal being small. I will try to refrain from using it in general, but if I do need to use it again, yes, I'll try to increase the size. Thank you. If you use one of the SourceForge installers, then you would need to open up a terminal and execute whichever of these calls corresponds to your operating system. And I'll say, and this is where I will rely on our TAs for today. These paths are kind of moving targets. So you may find when you go and look in your CompuCell installation that there are some minor details in here. What you are looking for is some executable called activate. And when you call this, you should find that the Conda environment for your CompuCell installation is then activated. So open a terminal, and if you're in the group that installed directly from Conda, just activate your Conda environment using the name of the environment. If you use one of the SourceForge installers, open up a terminal and locate wherever this activate executable is in your CompuCell installation and either issue call or bash, depending on if you're on Windows or Mac or Linux. Now, having accomplished that, you can code along with me directly in your browser using Jupyter Notebook by issuing the command Jupyter Notebook. Now again, that is after having accomplished this first step. So the Conda environment should have Jupyter Notebook already installed. So you activate the environment in whichever way is relevant to your installation and operating system. then issue the command Jupyter Notebook, you should find that a browser opens up and you land at the Jupyter Notebook homepage. You can just create any notebook that you want, and that's where we'll do all of our work together. So I'll give everyone a couple of minutes. Feel free to rely on the TAs in the chat. They are here to help you. And again, if this becomes some big mess that distracts from the real goal here, which is to get you acclimated to what all is available in the Python API, then I'd say don't worry about it. You can email me or reach out to one of us afterwards. We can help you get set up, and then you can go back along through this at your own pace. I am not going to use Jupyter directly. I'm going to work in VS Code. You know how to set up VS Code, then have at it. I don't want to spend the time on it. So I'll say, if you can do it, then go for it. If you don't know how to do that, that's fine. Use Jupyter Notebook. All of the work will be the same. While people are trying to get set up, say if you did install directly from Conda and you prefer using VS Code, this is as simple as creating an ipynotebook file wherever, and then in the top right hand corner, just selecting the corresponding environment, and that's your entire setup. All right, so let's just go ahead and get right into it. So a CompuCell simulation is always contained, at least for our intents and purposes here. A CompuCell simulation is all contained within one specific Python class called CC3D SimService. Now, Lorenzo is going to get into the guts of this a little bit more in the next session. There are all sorts of exotic things you can do with SimService. And actually, James mentioned the work integrating some CompuCell with Vivarium. So James, after you mentioned that, I pulled this up. So here's an example of what you can do with CC3D SimService and actually other sim services. CC3D SimService is built on a library called SimService, and you can see an example here in the publication coupling CompuCell with a totally different simulator called TissueForge, which is another package that some of us developed. So this is coupling CompuCell with a particle-based model simulator called TissueForge, where TissueForge is representing subcellular elements of the cell, and there's a two-way coupling between the two. Now, there is an ongoing project currently to deploy the CompuCell sim service as a process within the Vivarium ecosystem. Actually, CompuCell, TissueForge, and just arbitrary services. So for those of you who might be interested in Vivarium, it is already straightforward to take what you'll learn today and put it in a process in Vivarium. And in the long term, I'd say probably in the roughly near future, general support for CompuCell and other simulators deployed like CompuCell will be available in Vivarium. All right, quick shout out on that. You can always create a CompuCell simulation though with this CC3D SimService class, and there's a straightforward way to get it directly from the package. So let's go ahead and test. For those of you who are up and running, let's do a quick test in your working Jupyter Notebook. Just to make sure that you're up and running, just try import CC3D and return. Okay, so you should have found if you tried import CC3D, maybe it was a bit slow to load on the first execution. After that, it should be relatively quick. But you should be able to do import CC3D, all lowercase, and get no errors. Now to get the CC3D sim service, and you don't need to do this just yet, we've got a command here for importing the CC3D sim service class from a specific location. This is the template here for how to create and launch a CompuCell simulation that's in a state that's ready for execution. So you just import the CC3D sim service class, instantiate an instance of it like what you see here, not necessarily with any arguments. You add some model specification thereafter, and then just walk through these simple steps. Run, init, and start. If start seems familiar, that is the same as the start method in your Steppables. And for your reference, if you happen to have registered some Steppables with your CC3D sim service, you'll find that their start method is called when you call the start method on the corresponding CC3D sim service. Okay, no need to do this for now. We'll come back to this just for your reference. This is the goal here, is to fill out this pattern, add some model specification, and then thereafter we'll do some interesting stuff to execute and visualize, and if we have time, even control a simulation interactively in your Jupyter Notebook. All right, so let's start with a clean slate and get right into it. So there's a one-to-one mapping, I'd said in the beginning of our discussion about model specification between the Python API and the CC3D ML. And you can see an example of this here on the right-hand side of my screen. So here's the POTS markup language specification. It's pretty bare, but should look familiar. And here below it, in this box that says Python, this is the corresponding Python API specification to do literally the exact same thing. So everything that's specified here in the markup language snippet here is exactly accomplished in Python using the corresponding code here at the bottom. And all of the specification for the Python API is in one Python module, and that is cc3d.core.pycorespecs. Everything to instantiate or to specify a model, initial conditions, diffusion solvers, everything. cc3d.core.pycorespecs. Now we just do this one by one for every markup language specification. There's a corresponding PyCoreSpecs instance, and you just go down the line, much in the same way as with the markup language, but instead you create corresponding classes in the Python API. You fill out your specification either in the constructor or in methods defined on that instance thereafter, and do all the same things as you would ordinarily do in the markup language, but instead purely in Python. Now, the interesting thing about the PyCoreSpecs is that they provide an additional functionality that's not available through the markup language, which is that you can access the original model specification from within your Steppables and make changes to most of them during the simulation. We'll get into this a little bit there here in a bit, but just for your reference for now, once once your simulation is actually executing, you can include in your Steppables to refer to PyCoreSpecs instances that you use to define your simulation, and then you can set parameters and change things and then make the simulation reflect those changes. That's a very simple example. So all Steppables have a property called specs. So in a Python Steppable method, you could say self.specs, and this will refer to everything that you use to define your simulation. In this case, this simulation used the ExternalPotential plugin, and the ExternalPotential plugin that was used to specify the simulation is available on the specs property with the name ExternalPotential. So all of the properties, all of the parameters and whatnot that are defined in the ExternalPotential, you can get that from a Steppable during a simulation and then make changes and let CompuCell know to reflect those changes. That's done with just a method called steer. So here's an example of what this looks like. This is somewhere in the step method of some Python Steppable. This is getting the ExternalPotential PyCoreSpecs instance, getting the specification for a cell type called cell, and then setting the model parameter x equal to 1. That's what this line here does. And then after doing that, and maybe some other things, they just let CompuCell know to reflect those changes by saying steer on the specification that was modified. Now, not everything through the Python API is steerable, which is to say not everything in CompuCell in general is steerable. But you can easily identify when you've tried to do some steering on a part of the specification that's not steerable, because your simulation will throw very specific kind of exception called steerable error. If you call steer to try to make a change during simulation and you get a steerable error, then you know that the specification you're trying to modify cannot be changed during simulation execution. Now, there are some occasions where that's just by virtue of that no one's implemented it yet. In other cases, it's just not possible, but this is a good opportunity for some feature requests. If there's something about your simulation that you'd like to be able to steer, you want to see this go away, then you can create an issue on the GitHub repository or email me or any of the other CompuCell developers, and we can figure out whether or not that's possible. Okay. Let's do some coding. So you can think of this much like how you've been thinking about building your simulations through Twedit in the markup language. Just go down the line and select which plugins and steppables you want, add them to the markup language. But now we're going to do so in Python, and we're just going to walk through this one by one. So every CompuCell simulation needs a POTS specification. The POTS specification in the Python API is through a class called PottsCore. So you can fill out exactly what is shown here. The snippet on the right, what we're going to do is create a simulation that has dimensions 100 by 100 by 1. So this is going to be a two-dimensional simulation. We'll use a neighbor order of 2 and impose periodic boundary conditions. And it's done like follows. From cc3d.core.pycorespecs, import PottsCore. And then you can create an instance of that. I'm going to call it PottsSpecs equals PottsCore, and then you can just fill out the specification through the constructor. PottsCore has a ton of details that you can specify optionally. I believe there are defaults for quite literally everything that you could specify. Here we're going to particularize by saying dim x, which is the dimension along the x direction, equal to 100. Likewise, dim y to 100. We don't need to say dim z equals 1 because the default for dim z is 1. But we do
Hey,
need to...
TJ,
Go ahead, Hayden.
zip in that text a little bit. It's pretty small on the screen share.
Yeah. I can remember how to do it.
Yeah, I was laughing earlier when somebody asked to zoom in on the terminal in Windows. That's a non-trivial exercise.
Here we go. I think this should work.
Yeah, that looks better. Thanks. Maybe one more.
One more. How's that?
Yep, that looks good.
Great. Thank you, Hayden. Okay, so we specify dim x and dim y equal to 100. Specify neighbor order of 2. These are all terminology as you currently understand them based on your time in this workshop so far. So no explanation here necessary. Neighbor order equals 2. And then we want to give periodic boundary conditions along the x and y directions. We can do so by saying boundary x equals periodic, capitalized. Boundary y equals periodic. That's it. Now you should find that when you run that, you should successfully instantiate that PottsCore. A little slow restarting. Here we go. And ooh, that's slow. There we go. It's not particularly data intensive. Hopefully that doesn't stay slow. Okay, so if you got through this like me, then you were successfully able to instantiate the PottsCore instance. Now we can move on. Let's document our code as we go. I'm going to add a little markdown in the cell beforehand. I'm just going to say define pots, just to remind myself of what I'm doing here. Now let's define a couple of cell types. Find cell types and a little markdown. Cell type plugin has a PyCoreSpecs instance called, maybe you guessed it, cell type plugin. So from cc3d.core.pycorespecs, import cell type plugin. I say, if you don't like doing this import over and over and over, I'm doing this so that it's clear what's happening. But if you don't want to do this over and over and over, you can, at the very beginning of your script, just say from cc3d.core.pycorespecs import asterisk. That's perfectly fine to do. Again, I'm doing this for each class just to be perfectly clear about what all's being imported here. Okay, from cc3d.core.pycorespecs import cell type plugin. Let's define two cell types. And just to exercise that we're working in Python directly, let's first do so by defining two cell types, but just in a Python list. We'll call them type 1 and type 2. So I'm going to say cell underscore type equals, and then in the Python list, type 1 and type 2. It's pure Python. And then I'm going to create a cell type plugin instance and just say cell underscore type underscore specs equals cell type plugin. And ordinarily do just type 1, type 2, yada, 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 as many cell types as you want to name. But in this case, since we already have it defined in a Python list, we can just say star cell type. And actually, I'm going to correct this and say cell types. Cell types equals, and then a Python list, type 1 and type 2, cell type plugin, just pass the list. Now you can check to make sure you did this correctly by executing. I got no error. Hopefully you get no errors as well. Let's continue. Now let's add a couple of actual bits of model specification for affecting cell behaviors. First, let's add a volume plugin so our cells don't disintegrate. So add a volume constraint and a little markdown. Volume plugin is defined in the class volume plugin. From cc3d.core.pycorespecs import volume plugin. And let's exercise our pure Python a little bit more. Let's define a target volume of 25 and a volume parameter, which is the Lagrange multiplier, equal to 2. And let's first declare them just as Python variables. Target volume equals 25. Say lambda volume equals 2. I just create a volume specs instance. Sorry, a volume plugin instance. I'm going to name that variable volume specs. Now in this case, we're going to get a little bit fancy and exercise some of the features that are available on PyCoreSpecs themselves to make this kind of expressive and Pythonic. So the cell type plugin instance has some iterators where you can iterate over all of the cell types that are defined in its data. And what we want to do is create a volume plugin term for each of our two cell types. But let's do so by iterating over the cell types in the cell type plugin instance. So let's say for cell type in, we'll do cell type specs dot cell types. This will iterate over all of the names of the cell types in the cell type plugin instance. Now we don't want to define a volume plugin set of model parameters for the medium, and one difference between the Python API and Player or specification through the markup language is that in the Python API, you don't have to tell CompuCell that the medium is there. So the medium is implicitly defined. And you can't create a CompuCell simulation without the medium, so it's just automatically defined for you in the cell type plugin. Even though we didn't tell it medium when we specified the cell type plugin. This is important to note here because when you iterate over the cell types in the cell type plugin instance, you'll find that the medium is in the iterators. So we want to say that for cell type in our cell types, if cell type does not equal medium, then let's define some volume plugin parameters. So the volume plugin instance has a method for creating a new, this is defining the target volume and lambda volume for a named cell type. You can do so with the method param_new. Volume specs.param_new. And you just tell it cell type that you're specifying some parameters for. And then by keyword, target volume equals our conveniently named variable target volume. And likewise for lambda volume, our also conveniently named variable lambda volume. So we're iterating over all of the cell types in the cell type plugin instance. We are only defining parameters for cell types that are not the medium, which is implicitly defined in the cell type plugin. And then for each of those cell types, we are using the param_new method, specifying the cell type that we're adding parameters for, and then the target volume and lambda volume. You should find when you run this that you get no errors. All right. Let's do another one. Let's add some contact energy. Add contact energy. It's Markdown. Contact plugin, as you know it in the markup language, is available through the class contact plugin. So from CC3D.core.PyCoreSpecs, import contact plugin. Now, just to keep things simple and straightforward, we're just going to apply contact energy to all interfaces. We're not going to do any differential adhesion this time. In this case, we're actually going to do a cell streaming simulation. So in this case, we want to have some contact energy, but we'll just make it homogeneous. So let's declare one Python variable contact_energy. We'll set it to 10. We'll just apply that to all cell types. Or all cell type, what pairwise, all pairs of cell types, as well as the medium. And much like you have done many times in markup language, I'm going to define new parameters for each pair of cell types or cell type and medium. You can do this first by creating a contact plugin instance. Let's say contact specs equals contact plugin. An optional argument to pass here is the neighbor order of the contact plugin. If you pass nothing, it'll be 1. Let's do a neighbor order of 2. And then much like with the volume plugin, you can define new parameters for the contact plugin using a method on the contact plugin instance called param_new. And in this case, we're specifying the 2 types of cells and the corresponding energy. We can do this with keyword arguments. So the keyword arguments, type 1 equals Let's just start with the medium. So this is the first cell type of the interface. Type _2 equals, and we can refer to our previously defined Python list. It's done up here. Cell types equals type 1 and type 2. Those of you who like to get really expressive with your Python, maybe you're already spotting ways that you could do this in maybe a more Pythonic way. We're just going to do this explicitly. Type 1 equals medium, type 2 equals cell types first cell type in our cell types list, and then define the energy. Here is our variable contact energy. Now you can copy and paste and blast your way through this. We want to define the same thing for our second cell type with the medium, as well as cell type 1 with type 1, type 1 with type 2, and type 2 with type 2. I'll give everyone maybe 30, say 60 seconds to knock this out. You can just copy and paste and kind of go down the line and fill this out. So type 1 with the medium, type 2 with our second cell type. Now with our first cell type and our first cell type. First cell type with the second cell type. And second cell type with second cell type. And if you're with me and you execute, you should find you get no errors. Maybe noticing Jupyter reporting an object that's returned from this param new call. Each of these calls actually returns a Python object where you can further customize some of the details of each of these parameter entries. We are not going to go there today, but you can go down quite the rabbit hole with diving into the details of what's returned by each of these param new calls. Okay, give everyone 10 more seconds and then we're going to continue. All right. Hopefully you're with me. If not, that's fine. Just observe, maybe take some notes, and you can go back through this with the recording on your own time. No problem. Now let's add some cells. I think we're going to get to some actual simulation execution after this. So we're going to use the uniform-initializer. Let's make a note what we're doing. Add some cells. The uniform-initializer steppable is available in the PyCoreSpecs with the name uniform-initializer. And just like everything else we've worked with so far, just instantiate that. I'm going to call mine UniformInit for uniform-initializer. Just instantiate that with no arguments. And then for the uniform-initializer, the specification is to define different regions. The uniform-initializer, it's defining 2 points that define the slab of cells. You can define the width of the cells and the phenotype consistency of that region. That's reflected here. So you can say with the instance of your uniform-initializer, you can use the method region new, and then just in the arguments, you can specify all of the stuff that maybe you recognize or remember from the CC3D ML. So let's say width equals 5. Define the 2 points of the region, PT_min for minimum point. Let's go 0.000. For our maximum point, PT_max equals let's go a little Pythonic. What we want to do is create a region that covers the entire simulation domain. And just so we don't have a bunch of redundancy where maybe we make changes later and have to implement those changes throughout, instead, let's use the data that's defined in our PottsCore instance. That was called PottsCore_specs. If you're following along with me to the letter, I say PottsSpecs.dim_x, PottsSpecs_dim_y, and you can either say PottsSpecs.dimZ or just one. And then lastly, define the cell types that go in this region. This is just a list of names. So cell types is the keyword argument, and we'll just refer to our conveniently named Python list cell types if you're following along with me. So I again have my cell types defined first in a Python list. And I'm just going to use that directly here. So this is defining one region with cells of width 5, go over the entire simulation domain, referring to data that's defined in the POTS core specification, and then just both of our cell types. If you're with me and execute that, you should find that you get no errors. This also returns a Python object that has more information that you can particularize about this region. We're going to skip over those details for now. I'll give everyone 10 seconds. All right. Time for the ultimate test. Let's see if we can get a simulation going. Create a new cell and some markdown. I'm going to label this one as create a CC3D simulation. This is where the rubber meets the road. We're going to go back to the CC3D sim service topic that we discussed earlier. So we want to get the CC3D sim service instance. We can do so by saying from cc3d.CompuCell setup.cc3d caller import cc3d sim service. Again, what we instantiate in this class will be the simulation. So everything in the simulation that will execute, will instantiate it, will orchestrate it, will do things with it. It's all in the instance of the CC3D sim service. Now we instantiate that. There are all sorts of ways that you can particularize how the simulation is instantiated, but you don't have to specify anything. So we'll just use no arguments in the constructor. So we just get a typical CC3D sim service. And this thing is empty. There is nothing in this except just simulation power ready to be populated and exercised. Now, how we do this is we take all of the PyCoreSpecs instances that we have created all the way up to this point. And analogously, we can also define Steppables in exactly the way that you have done in this workshop to date. And you can register your PyCoreSpecs instances as well as whatever Steppables you may have defined. We add those to our simulation through registration processes. So we say CC3D, if you're following me, I named my variable CC3D sim. The sim service has a method for adding PyCoreSpecs, register_specs. And you pass just a list of all the PyCoreSpecs instances you want to be populated in the simulation. This is analogous to launching a CompuCell simulation with a CC3D ML file. Everything that's in the markup language is assumed to be added into a simulation. In this case, you explicitly specify which specifications you want registered with the simulation to create stuff. And so let's just add everything that we've instantiated so far. So let's add our pot specs, add our cell type specs, add our volume plugin. That was volume specs. If you're following closely with me, add our context plugin, and add our uniform-initializer steppable. And that's it. That's all you need to do to get all of your specifications populated in the CompuCell simulation and ready for instantiation and execution. Now, it's important to point out right here, maybe just as a reminder, all of the PyCoreSpecs stuff that we've instantiated up to this point, this is all just specification data. There's no actual simulation in any of these PyCoreSpecs. This is just a different way of representing the kinds of data that you make in your CC3D ML specification. So there is no simulation done with any of these. This is just a Pythonic way of specifying what all should go inside a CompuCell simulation when it's created. All right, now let's walk through the template. So register our specs. If you had any steppables, you would register them here. We're not going to do any steppables because you've had lots of practice with them to date, but they function in all the same way with a few additional bells and whistles when using the Python API that we previously mentioned. Now let's launch this thing. CC3D underscore sim.run. For those of you who like the gory details of the software, this instantiates the simulation in memory. CC3D sim.init. This will go through all the initialization procedures. CC3D underscore start. This will call whatever steppables you register, this will call your steppable start method. And if you're with me, give it a try. Execute it. Oh, I got a bug. Try to rerun it. I think this is a cache issue on my side. Yeah. Sorry about that. It's a different version of CompuCell, just cached. I was doing some debugging earlier today. Okay, so if you were successful, like I happen to be here, then Jupyter maybe is just reporting a Boolean true. Each of these methods will return a true or false. True meaning that it was successful, false meaning that it failed. Just going to assume that they're all successful, so you may see a true value reported in your Jupyter Notebook. But this is ready to go. There's a live CompuCell simulation in your Jupyter Notebook right now, ready to be executed. Give everyone 10 seconds for anyone who may be scrambling to either get a question answered or get some code up to date. Okay, let's visualize. I'm going to pull up a graphics pane like what you have been using in Player. You create visualization panes to check out a simulation, show different fields, move the view, whatnot. So there is an equivalent in the Python API. And I'll say this is available both in pure Python and the Jupyter Notebook. So if you run this same kind of code, there are a few things here that are Jupyter specific, but it is also possible if you're working in pure Python to pull up a visualization window or set of windows, and you can still visualize a simulation as if you were in Player, even though you're not. So we're going to go through just the basics of how to set up one of those visualization frames and have them visualizing the simulation as it executes. So let's create some new cells, one for some code and one some markdown to leave a note. Let's say visualize the simulation. Okay, we are going to use some additional Python library stuff. We're going to use IPython, which those of you who have not really worked much in Jupyter Notebook, this is a standard way to visualize things in Jupyter Notebook. So most Python packages that have Jupyter support will have some sort of display support like this. You can say from ipython.display import display. This is in no way CompuCell specific. This is Jupyter Notebook specific. So from ipython.display import display, and we're going to create a visualization frame. Follow really closely with me. You can name your variable frame underscore cells. We're going to capture the output of a method called visualize that's on the sim service. When I say CC3D sim.visualize, this tells CompuCell to create a visualization pane and give me a reference to it so I can specify things about that frame. So here I'm going to say frame underscore cells equals CC3D sim.visualize. You want to do a little bit of customization here. There are, maybe you guessed it, all sorts of ways you can particularize this frame just through the constructor. One really common way, you don't need to do this, but one really common way to customize this is to reduce the number of simulation steps that are visualized. So if you say plot underscore freq, FREQ equals 10, this will visualize every 10 simulation steps. It's not noted here. You don't have to do this, but this will make your simulations faster. Now, this frame cells has a whole bunch of properties and methods defined on it to specify all sorts of things like what fields are shown. We're going to just customize very quickly as a demonstration. We're going to control how wide the frame is on our screen. We're going to do so by saying frame cells dot window underscore width underscore percent. Set the percent of the window that's occupied by the frame to 25%, 0.25. If you don't do this, and you don't need to, this is just the frame will occupy the entire width of your Jupyter Notebook. And then we can do frame underscore cells dot show. That tells the frame to display itself. And we're going to do one more little fancy thing here, which is very Jupyter specific. We're going to create a simulation control button that lets us pause and resume simulations just like you do in Player. It's just a very simple ipywidgets button that's connected to controlling the simulation. And the method to create one and show it is Jupyter run button. So this is defined on the actual CC3D sim service. If you say, actually, let's display it. So let's first say display. This is our IPython function that we imported. So display, and then refer to our CC3D sim service instance. Say CC3D sim dot Jupyter underscore run underscore button. No arguments. So imported display from IPython. We created a frame for visualization using the CC3D sim service method visualize. We set the percent of the width that will be occupied by the frame to 25%, and then told the frame to show itself. And then along the way, we created a run button to be able to pause and resume the simulation. If you're with me, go ahead and try it. See what you get. There you go. Hopefully this looks familiar. So if you got the result that I got, then a pane like from player shows up. We're looking at a two-dimensional view of a simulation where cells occupy the entire domain according to our uniform-initializer steppable. We have our two cell types. Mine are shown as white and green. If yours are different colors, that's no problem. And you should have a little run simulation button underneath. And you should find, if you press it, that you have CC3D executing in your notebook. Now I should say some of the machinery underneath this button is doing something for you that in many applications you would actually really be interested in doing yourself, which is stepping the simulation for you. So the CC3D sim service has a method on it. We pause. CC3D sim service instance has a method on it called step. No arguments. You should find that when you type CC3D sim.step, this should step your simulation. I'm only visualizing every simulation step, so maybe it's not showing. Yeah, there you go. You should find that as you call this repeatedly, in my case, I'm only showing every 10 simulation steps. But eventually, as I call this repeatedly, yeah, you saw that change. So this is the way to manually advance the simulation just one step. And underneath, if you have any Python steppables that you've registered, this is the time when your step methods are called. When you use this Jupyter Run button and you activate the simulation, it's not particularly magical. Somewhere under the hood, this step method is just being called for you repeatedly until you pause the simulation again. Now, if you're with me and you got this result, then congratulations. You are among the first handful of people to successfully launch a simulation through the Python API. This is certainly more involved than using Twedit. In some senses, in other senses, it's much more straightforward than specifying things in a markup language. Now, before we continue, because we have just over 15 minutes left, I'll just give a very quick shameless plug to some features that one of our developers, Pete, has put together. There is a plugin for VS Code that provides much of the same functionality that Twedit provides with the code snippets and all of that, but as a VS Code extension that can help you develop these simulations with a similar level of support as what you have in Twedit. But of course, in VS Code, you also have all of the other tools in the universe at your disposal. Debuggers, I mean, the sky's the limit. So if you've gotten to this point, you're starting to feel like, maybe this is a little more involved, than I'm interested in signing up for. There are additional tools out there, especially through VS Code, that can help you, bump along the way until you get more acclimated. for this. And I'll say for those of you who are really interested in like diving deep on doing some serious CompuCell development, my official opinion is that this is absolutely the way to go. We have 15 more minutes. Let's see if we can get just a little bit farther and see if we can get through showing off one of the many very cool ways that you can use CompuCell, specifically in the Jupyter environment. Let's add some force and make these cells move. We're going to blast through this a little bit. Hopefully you've caught on to the pattern. If not, that's totally fine. Again, you can do this at your own pace afterward. Let's go back up in our specification and let's add a force to our cells using the external potential plugin. I'm going to go up and say, I'm going to add it after my contact energy. I like to keep things kind of grouped together conceptually. So I'm going to create a cell after the contact energy. You can do this anywhere you want, so long as it's before where the sim service instance is created. Again, I'm going to do this right after the contact energy. Let's say add a force. And external potential plugin is also available in the PyCoreSpecs under the name external potential plugin. And this one we also instantiate. I'm going to call my variable external potential specs. Just instantiate it, no arguments. And then this class also has a method for creating parameters by cell type. And that method also is called param_new. So this is creating entries in the external potential plugin by cell type. And here, let's say param new, and for each of my cell types, which again in my notebook is defined in the Python list cell types. Let's say my first cell type has an external potential X component equal to -10. And then for my second cell type, type 2, I'm going to say that it has an X component of 10. So they're facing opposite directions. So external potential specs dot param new, and then each of our cell types, one with X equals -10, the other with X equals 10. Now let's go down to where our PyCoreSpecs instances are being registered. This is not order specific, so you can add this into your list of registered specs anywhere you want, so long as it gets registered. And then let's restart the notebook and rerun. All right. All goes well. And after restarting and rerunning the notebook, it should be back to where we were previously. The CompuCell simulation that's visualized and waiting to be let loose. And you should find that when you press the run simulation button, and now you have what looks like New York City traffic. Got cells of one type moving to the left, pushing past cells of another type, moving to the right. This next little bit is a little more involved, and I don't think we have enough time to do it together. So if you can follow along with me, then you are more than welcome to. Otherwise, I want to just show you one more step here in developing this notebook. Again, the slides will be shared. You can do this on your own. We're going to step a little bit more into integrating CompuCell with external tools. And this does have a bit of a learning curve that I don't want everyone to get tripped up on. So with these last few minutes, let me walk you through setting up something kind of fancy and cool that you can set up yourself on your own time, or if you've done this kind of stuff before, then have at it. Maybe it'll look familiar. But check this out. So Player has a whole set of tools for steering, setting up sliders and switches and whatnot to be able to control your simulation in real time, modify parameters, observe the effects and whatnot. So you can do the exact same thing with the Python API, except using the visuals or the user interface like widgets and tools of your choice, presupposing that you know how to work with those tools. And that's where the learning curve is here. What I'd like to show you very quickly here is how to set up steering with a widget, but not using a CompuCell provided tool, but instead just using ipywidgets, which is a very popular Python package specifically designed for setting up user interface like widgets and tools in a Jupyter Notebook. So this is CompuCell getting integrated with a very common package out there to do much of what's provided for you in Player, except that once you know how to do it yourself, you can build whatever widgets and interactive components that are relevant to you or maybe of interest. So here's the example for your reference. If you want to go do this in your own time thereafter, we're going to use ipywidgets to create one little user interface widget to control the force that's acting on one of the cell types. So we're going to do what we have previously referred to as steering, just setting a model parameter while the simulation is executing. And in this case, we're going to do that steering with a slider. So really wherever you want, if you're going to try to bang this out with me, you can do this anywhere really before creating the CC3D simulation. I'm just going to do this in my notebook right before I create the simulation. So I'm going to create a markdown cell and just say add control. And I use the ipywidgets package. So import ipywidgets. This is a dependency of the CompuCell CC3D package, so this should be installed in the environment. You can check it real quick by just executing a cell that says import ipywidgets. First things first, with 7 minutes left, I'm going to blast through this. I'm going to define a callback that handles when a widget is changed. I'm going to call that CB for callback, external potential T1 to say they're going to handle changes that affect the external potential plugin specification for type 1. This by definition, using ipywidgets, has one argument called change, and we're going to give this function to an ipywidgets instance to implement effects when we change the ipywidget that we're going to set up. And also using ipywidgets machinery here. This is all ipywidgets specific, and this is well documented in their stuff. None of this really is anything that we control. It's just using their stuff as they intended. So the idea here is that if this equals that, which you can refer to ipywidgets documentation if you're interested in the details. What's important is that under these conditions, we're going to make a change on our external potential specs. That's what we actually care about here. So under these conditions, when a widget calls this function and what it passes matches this condition, then we can refer to our external potential PyCoreSpecs instance, and we can change something about the specification for one of the cell types. And we can do that with the property cell underscore type. That refers to the specification per cell types, which you can use as a dictionary, like a dictionary. So when I say cell type and then pass the name of one of my cell types, this gives me back the original specification for the cell type that I gave the instance. Which means that when I say cell type, use the cell type that I'm referring to as a key and then .x, this gives me access to what I initially specified when creating the plugin specification in the first place. This is available here during simulation. And in this case, what I want is in my callback, so my ipywidgets is going to tell my function what is currently set on the widget. That's passed through here, and I'm just going to set my model specification to value. It says change the X component of the external potential specification for cell type 1 to whatever is the new value of the widget. And then importantly, call steer. This lets CompuCell know that there was a change and that the simulation should update accordingly. Now with 4 minutes left, just so we can show this off a little bit, we're going to have a little bit of time after this to talk a little bit more about whatever might be of interest to everyone. I'm going to create a slider. I'm going to call mine slider external potential T1. This is ipywidgets. I'm going to create a float slider, and this is all part of the ipywidgets library. It says nothing to do with anyone in this development team, just using their stuff as they distribute it. I'm going to initialize this slider with the value of my specification for my cell type of interest. So I'm going to initialize with this value. So that'll be the initial value of the slider. I'm going to put some sensible bounds on what we can actually set this to. I'm going to say that the value is constrained to a minimum of -10 and a maximum of 10. I'm going to allow values to be set in increments of 0.1. Particularity of ipywidgets is you can control when updates are issued. In this case, we want to say that continuous updating is disabled. So updates are only sent through this callback when changes are made to the widget. And we'll just give it a little bit of a description so we know later when we forget about what we did here, we'll know what this slider does. External potential for type 1. And then lastly, with 2 minutes left on the clock, we're going to connect our callback to this widget using its observe method, and I'm just going to pass a reference to the function. And another particularity of ipywidgets that need not concern us for now, names equal value. This should oh, the rest of the notebook needs executed. No worries about that. That's not a problem. And then last thing, and then we'll be done. We're going to display this slider down with our simulation. So we go all the way back down to our visualization, and along with our run button, display, just show it. If you're with me, I'm going to restart, clear all, and run it, and just see how far it gets. With 1 minute to spare. Now, if you followed with me and had any luck, you should now see a slider. You run your simulation. Looks as it did. Green cells, in my case, moving to the left, other cells moving to the right. I should find that when I change the slider, now they're all moving in the same direction. When I set the value to, say, around 0, now my cells are really just getting bullied, getting pushed by the other cells. And then if I set it back to -10, then it's back to the original specification. Now there's more prepared in the slides, but this is more than enough content for one session. I just want to say to conclude that the sky is the limit from here. I mean, this is just a tiny fraction of what all is available in the Python API per se, but opportunities for integrating with other libraries, for building your own notebooks, for building specific computational workflows, integrated other simulation capability that's provided by other packages. I mean, the combinatorial complexity is is very high in terms of what all you can do with CompuCell by developing your simulations purely in Python. Last thing, and then I'll turn it back over to James and Hayden. I believe Pedro is doing a lecture, I think on Friday, on deploying CompuCell in supercomputers and high performance computing environments. Have very heavily relies on the Python API, so you'll get another opportunity to see this capability in action. James corrects me privately and says that that's Thursday. So Thursday, I believe. So you'll get another whack at using these features in an actual relevant use case for high performance computing. Thank you all very much for your time. James and Hayden, I'll turn it back over to you.
If you weren't able to get this working, don't worry, you will not need this to use CompuCell and most of the things that you do. However, if you can do it, you're able to do much more sophisticated things in terms of cluster execution and also integration of CompuCell with other packages. So,
oh, why is this done in Jupyter? Okay, yeah, that's a great question. There are definitely a couple of reasons. For one, executing in Jupyter is interactive, which has a number of benefits on the development side. It's a lot easier to debug code, especially when you're working with libraries that you don't know very well. It's much easier to debug and develop code in Jupyter when you can stepwise, step through things. Secondly, much of the goal was of this session was to help you see the broader picture of CompuCell. Your experience through this workshop up until today has been through the graphical user interfaces, but in fact, that's just one side of CompuCell, and the software APIs are another major part of it. But using them in an interactive way, with real-time visualization and widgets and all of that, it hopefully is kind of familiar, even though the specification is very different. Whereas when you go to pure Python, the visualization is the real-time visualization is available, but it's not as immediately relevant as in an environment like Jupyter, where there's a lot of interactivity. In pure Python, that really is your space for doing simulations really fast, because the simulations in pure Python will be faster, much faster than in Python. It's also typically your space for doing more advanced things like automating parameter sweeps, automating, say, launching hundreds of simulations simultaneously on a supercomputer, Um, but it's not as stimulating as having a Jupyter notebook up and running it and seeing a window pop up where you can control it with a button. But aside from the Jupyter Run button, um, everything that well, the Jupyter Run button and the ipywidgets integration, aside from those two concepts, everything else that we did today it all applies in pure Python as well. Is it somewhere in our pipeline to incorporate discrete logical modeling? Well, that's a great question and a timely one. So we do have along the lines of antimony, tellurium, libRoadrunner to model the transcription regulation networks. Yes, so Pedro will do a session, I believe this time tomorrow, on another integrated simulator, much like libRoadrunner and antimony, but with Mabos. So Mabos is a stochastic Boolean network simulator, and CompuCell has an integrated version of Mabos that you can use in the same way as what you've been doing with the SBML, like ODE model simulators, but in this case with, yeah, stochastic Boolean network models. So that's a much newer feature of CompuCell that yeah, I'm quite excited about. And for transcription regulation and all of that, that's that was one of the main motivators for integrating that software. So great question, and definitely be there for that session tomorrow if you can. Yeah, James brings up BionetGen. There was a working prototype of BionetGen integration in the same way, but everyone involved got distracted. So that's on some branch that I haven't worked on in 3 or 4 years, but it is certainly possible. So Luis asked whether the lattice can be divided between several CPUs and GPUs. So CompuCell will divide the lattice over your CPUs depending on what you specify in your metadata. There is a metadata PyCoreSpecs instance, but we're in the CC3D ML, you define the number of processors to use. So CompuCell will divide the lattice accordingly, according to the best configuration that fits the number of processors that you specify. For the GPUs, so GPU support is being revived in CompuCell. It got quite dusty and eventually fell out of support for CUDA. We are in the process of reviving that. So when that gets revived, for starters, likely we will support CUDA supporting devices, and Mac is a separate challenge. And I should say the cellular POTS model itself doesn't particularly scale well on GPUs, but almost always the majority of the cost in CompuCell simulations is with the diffusion solvers. And those obviously accelerate quite well on GPUs. So yeah, we will have GPU support up and running again, hopefully in the next release or two.